Fraunhofer Institute. We'll be speaking on application of quantum annealing for scalable robotics assembly line optimization. Moritz, please start your presentation.
Thank you, and also thank you for the invitation. As you just said, I'm going to talk about quantum annealing on a manufacturing use case. This work was done during a project called Sequoia End-to-End, funded by the state of Baden-Württemberg, where we're located. And the scope was to find end-to-end applications where we can apply quantum computing to research on the applicability. And the use case we looked into here was this robotic assembly line optimization. And this ended in a paper which I wrote together with Marcel Albus, Jan Schnabel, and Marco Roth. We're all from the Fraunhofer Institute of Manufacturing and Engineering and Automation in Stuttgart. And Marcel and myself are also doctoral students at the University of Stuttgart. You'll find the paper at this link, or if you just scan the QR code, you'll also get directed to the paper. Let me motivate. What's the robotic assembly line balancing problem? Say you want to produce something in an industrial setting, you'll need some sort of an assembly line. There's certain steps that need to be taken to produce this good, and you'll have access to some machines. They all come at a different price point. Some are cheaper, some are more expensive. They all have certain capabilities of which tasks they can fulfill, and they also have different processing times for these tasks. There's a overall cycle time that has to be met. So like the time interval in which one of the products has to be finished and leave the assembly line. And we'll make a couple of assumptions to help us formalize this problem. One, we only produce one product, so it's always the same tasks that have to be fulfilled. The assembly line has a fixed cycle time, and we have deterministic task times per machine, but they can depend on the machine. Let's formalize this in a mathematical way. Let's start off by defining some variables. We have a certain number of tasks, and we have some workstations, some machines. We have the cycle time. Each machine has a dedicated cost. And we have a precedence graph, which defines in which way the tasks have to be fulfilled. And then, as I already said, each machine has a processing time for an according task. So my colleagues, Marcel Albus et al., they already formalized this as a linear program. So the goal is to minimize the equipment costs of the assembly line, so just the initial cost, such that with a couple of constraints. So the first constraint here, labeled number 2, makes sure that each task is processed exactly once. The second constraint, so here number 3, makes sure that the cycle times per machine are kept, and they also do this mapping of the assignment of tasks to machines, to workstations, to machines, to workstations. There's another cycle time constraint, number 4, which checks if the cycle times per workstation are satisfied. And then also the last constraint checks if the precedence graph is satisfied. This has been proven to be NP hard, and which is why we were looking into trying to solve this with quantum computing. So the first step was to reformalize this as a QUBO. There's a couple of steps we have to partake. First of all, we have a linear cost function, which we have to change to a quadratic cost function, which is fairly easy because we're working with binary variables. We have a couple of linear constraints. In QUBO, we can't have constraints, so we have to somehow add them to the cost function. And also we have to make them quadratic. This can be easily done with this transformation, which though introduces some Lagrange multipliers, which have to be added to the cost function. In this case, we have 4 because we have 4 constraints. And then lastly, since we didn't only have equality constraints, we have to change some of the inequality constraints to equality constraints by introducing so-called slack variables. They're just some sort of buffer variable, slack variable, as the name suggests, which allows us to reformulate the inequality constraints as equality constraints. By introducing these slack variables, we blow up the dimension of the problem. I have an example here. So in the linear program, we only have the machine workstation assignments Y and the task machine workstation assignments X. But we need to introduce 3 slack variables for constraints 3 through 5. If we say we have an example with 4 machine workstation assignments and 12 task machine workstation assignments, this introduction of slack variables already makes up the main part of decision variables in our QUBO. So our resulting QUBO has already 64 decision variables, which is huge and leads to a lot of problems later on. Another task we have to fulfill before we can optimize is the choice of the Lagrange multipliers. As I already said, in this case we have 4, and they sort of balance the cost function, the original cost functions, with the constraints, because now we don't have hard constraints anymore, but we have soft constraints, and to still fulfill these constraints, we have to weigh them enough so they don't get lost in the cost function. It's not straightforward how to choose these Lagrange multipliers. And so what we did was do an extensive grid search using D-wave anneal, so simulated annealing, and try to find the Lagrange multipliers that deliver us that yield us the most number of optimal solutions to our problem. Optimal solution in this case is defined as a solution that keeps all the constraints and then also minimizes the cost function. This is again for a small example, and we can see that there is a clear favorite of Lagrange multipliers, but it's not quite clear on how to find this via optimization. So that's why we did this grid search. So because these reformulations can be quite a bit of work, we don't want to do them every time by hand. So we wrote a Python tool which is available at this link, or if you scan the QR code, you can go there. And what this does is just offer a way to describe this assembly line balancing problem and then transform this to a QUBO with a couple lines of code. So it's very easy to use, and then we can use a QUBO to solve the problem. So because and we can use any QUBO solver we want. So for instance, we checked with Quava, but because of the size of the problem, or already small instances lead to quite large QUBOs, we weren't successful solving it with Quava. It's too large to simulate, and then also on the real hardware, we ran it on an IBM computer, it didn't get satisfactory results. So that's why we decided to use D-Wave annealers, and because we had a restricted computation time at D-Wave, we wanted to reduce the computation time there, and also already QUBOs of this size were quite hard to solve on a D-Wave annealer. That's why we chose to use QBsolve, which is also by D-Wave. I know it's deprecated, and D-Wave now offers this hybrid quantum annealing classical solver, which I suspect is just QBsolve running on their hardware, on their servers. And because we wanted to minimize the computation time there, we ran QBsolve on our own machines at the limitation that, of course, we had to consider communication with the server at D-Wave and with the quantum computer, and add this into our time budget. So what does QBsolve do? It's using a combination of partitioning larger QUBO instances into smaller QUBO instances and a taboo search algorithm, so a heuristic neighborhood search algorithm, to try to find solutions for QUBOs. Because of this heuristic search, this also again comes at the cost of solution quality, but we decided that we still wanted to use it because in small sample instances it worked quite well. Let's look at the results. So in the paper we only presented the results of example 1, but in fact we used 3 examples to sort of benchmark the method. Example 1 has 4 tasks, 2 workstations, and 2 available machines. A cycle time of 40, 3 edges in the precedence graph, 6 non-negative processing times, and this leads to the linear program dimension of 16 decision variables, and we yield a QUBO with 64. So this is also the example from before. And then we have some larger instances as well, the largest being with 186 decision variables in the linear program, and 494, so quite large instances in the QUBO. So as we all know, we can't directly map the QUBO to the quantum annealer because of connectivity issues. So if we have some variables connected that are very far apart, we have to sort of implement this like row of qubits to connect these two. So the actual QUBO dimension on the hardware blows up. I don't have the exact numbers, but already for the 64 qubit QUBO, this would go well into the 300s for our case with our connectivity. So this again is why we needed the the QBSolve algorithm. So let's look at the results for example 1. We were looking for, we were creating 1,000 samples, and we were looking at which solution was valid, so which solution satisfied all the constraints, and then also we were looking at the costs. Here are depicted the top 50 samples sorted by occurrence. So on the left, you can see the occurrence of each solution, and if it's green, it's a valid solution, and if it's red, it's an invalid solution, so it doesn't fulfill the constraints. And as we can see, we have definitely more valid solutions than invalid solutions. So this already tells us that the choice of Lagrange parameters was fairly well. And also, if we look at the costs, we can see that already the optimal solution occurs a couple of times, and already in the 1, 2, 3, 4, 5, 6, 7th position of the samples, we have the optimal solution according to costs. So for the first example, this worked quite well. Let's look at the results for the second example, and here we can already see that it doesn't work so well anymore. Our suspicion is that it's just according to cuboid dimension, and that the loss landscape is too complex for maybe the QBSolve algorithm to solve it, or just the nature of the loss landscape is too hard to optimize. So what we can see here, that we mainly sample invalid solutions, and the first valid solution is only at position 181. So yeah, we can see it's already not working so well anymore. And if we look at the Lagrange multipliers for example 2 and 3, we can see, yeah, for example 2, we can still find some optimal solutions, but they are much more scarce. Earlier, before, with the optimal combination, we had 65 optimal solutions out of 1,000, and now it's only 18. And then, for example 3, with the Lagrange multipliers and the D-wave anneal, so simulated annealing algorithm, we can't find any optimal solutions anymore. So this also speaks for the suspicion that just the optimization landscape of the problem is too hard to solve with simulated annealing. In this case, we can't speak for quantum annealing, for example 3, because we weren't able to run it on a quantum computer without the proper Lagrange multipliers. We wanted to continue to compare the results with a couple of KPIs, which were defined in the original paper on the assembly line balancing use case. So just to check for solution quality. So the things we checked, or the things we looked at, was the cost for the equipment of the assembly line. Then we didn't look at workstations, because in our formulation we already had to prefix the number of workstations to use. And then we looked at the amount of purchased machines, the workload, which is like the idleness of the assembly line. So it's better to have few machines idle while running the assembly line, because that would speak for us having too many machines, maybe. And then also we looked at the runtime, so the solution runtime of the optimization. So here you can see again the 3 problem instances, and then we compared the wave anneal with the D-Wave quantum annealer in combination with QBsolve, and then with the linear program solution done with Gurobi. And here you can see for the first problem, we can find the optimal solution with both simulated annealing and quantum annealing. For the second problem, it's already harder to find the optimal solution with the D-Wave system, but we can still find it with the simulated annealing. And then for the third problem, we couldn't find any solution. That's why there's only the Gurobi stated here. And then also in the runtime, we see that as of now, it's not really competitive, but still we might have some scaling advantages if the hardware improves. For the other KPIs, max efficiency, we see that we match the solutions of the classical solver with our quantum solver and simulated annealing. Here we even find solutions that improve the efficiency, which are solutions that might be suboptimal in a different when looking at a different KPI. So this doesn't necessarily mean that we're better than the classic solution, but if we were to produce some samples and then decide to look at a different thing, we might have the advantage here since we have multiple samples rather than just one solution which we yield by the linear solver. And then the amount of equipment per problem and solver. So the amount of bought equipment, again, in problem 1, we match the results of the classical solvers, and then in problem 2 already we struggle with the quantum annealing. So what do we take from this? What are our take-home points? We were able to formulate the problem as a QUBO, and were successful in demonstrating on a toy example, very small example. And we might suspect some scalability benefits with quantum annealing. And also because we're solving a sampling problem rather than an optimization problem, we might get some benefits for multi-objective optimization by already having all access to more samples. And we kind of see our work as a foundational starting point for future research. If quantum hardware improves, researchers in the field of manufacturing can look at this work and try to solve their respective problems with our approach. We encountered quite a couple of limitations. First, by introducing these Lagrange multipliers, we introduce another step of optimization, which makes the problem harder to solve, and also by increasing the problem dimension by introducing the slack variables. We also first off make the problem harder to solve, and then also more prone to errors if we solve it on a quantum computer, which right now is affecting the scalability on current quantum hardware, but we suspect it not being a problem with further research on hardware. And then also another limitation is that with our approach, we have to fix the number of workstations quite conservatively, because if we choose too few workstations to generate or to work all of our tasks, we can't solve the problem. But if we choose too many workstations, we can solve the problem, but we might get suboptimal solutions. And also we need a lot more a lot more decision variables and larger qubits because the number of qubits scale with the number of workstations. And also the hybrid approach, so QBSolve, which we used in this work, might introduce some limitations on solution quality. So because we don't solve the full QUBO on the quantum annealer, but with this hybrid heuristic search, we might get suboptimal solutions. It worked for the small toy example, but it already didn't work so well for the larger instances. So this is something one could look at in the future. If the quantum hardware improves, we could definitely get better results with full-scale quantum annealers. And that's it from my side. Thanks for your attention. And I'm looking forward to questions.
Yeah, thank you, Moritz. Any question or comments? I have some questions. So the problems you utilize in this study, so do you generate by yourself? What are their standard program instance in this field?
So we have some real world instances. So for example, the example 3 here was derived from a real world instance. These two were self-produced problem instances because this one was just too large to tackle, at least for development purposes. We had to produce some smaller instances, but we have access to real world examples.
So can you guess the how much the larger, let's say the quantum annealer or Ising solver we need to help the real problems?
So what we've found is that without any, because we didn't look a lot into tuning the quantum annealer hyperparameters. We just used the default ones because none of us were experts in the hyperparameter optimization. We were able to solve in the scale of 30 to 40 qubits, which and there we got satisfactory results on the quantum annealer. But so for larger instances, so say here 500, so it's sort of an order of magnitude larger.
Okay. Yeah. So under other aspect, so you mentioned that this is not just a single cost function, but the nature is a multivariate optimization. So
yeah, so this is this sort of arose in our group discussing it, that because Marcel Albus, one of my co-authors, he works a lot with these like assembly line balancing use cases, so like greenfield process, brownfield process, and he said that sometimes different KPIs can be interesting. And this could be a benefit, that because we're solving a sampling problem, not a like straightforward optimization problem, but we generate samples. We could use classical search algorithms or something to to look in these in the generated samples for optimal solutions, and then also if we have a couple candidates to choose from, we can look at different KPIs to choose our favorite from the other ones. So this could definitely be a benefit of this of the sampling nature of quantum annealing.
So you can draw the palette front line utilizing those variables.
Come again,
That's
sorry?
yeah, so in a multivariate optimization setting, we can draw the palette front that balance the two or more optimal the target cost functions. Yeah,
Yes.
so for that purpose, yeah, this approach may help. I see.
Yeah. So yeah.
Okay. Any other questions? No. Okay. Thank you again, Moritz.
Thank you too. And have a nice day.
Nice day too.
Bye.
Bye.